Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called torque. So what we're looking at here is we've got some sort of bolt, and this is kind of the stereotypical torque example. If I want to turn this bolt, one way I might do that is I might go grab myself a wrench. And now imagine a pair of forces here applied to the end of the wrench. Now let me talk about why I labeled them the way I did. This one I called F parallel. The two parallel bars here are those two bars mean parallel. This one I'm calling F perpendicular. First, the $1,000,000 question is perpendicular to what? Well, perpendicular to this distance right here, the distance to the center of the bolt. You notice that this force is parallel with that distance, this force is perpendicular. Right? Now, in order to turn the bolt, this force will not cut it. This force will. That's because of these two forces, this one creates the quantity that we need to get that bolt to turn, which is called torque. Torque is force times distance, but there's a little qualifier. The force has to be perpendicular to the distance, always. So in this example, if I go ahead and put that green distance back here, d, then the torque is going to be the perpendicular force times the distance. Now let's talk units. Force times distance, this would have units of Newton meter, or in the SI system this might have, in the English system this might have units of pound foot or pound inch or something. I'll go ahead and stick with this. Now the Newton meter should sound familiar. You might say, oh, that's a joule from work or kinetic energy. Torque looks like work, force times distance. It does, but there's two really big differences. Difference number one, when you calculate work, you use the component of a force parallel to the displacement, not perpendicular. That's one difference. Second difference, for work, there has to actually be a displacement. It's not just a distance, it's a distance moved. Right? And third difference is that torque is a vector and work is a scalar. So generally speaking, in most problems, clockwise, counterclockwise is good enough for the direction. So in this example, the torque would equal F perpendicular times whatever d is, and the direction would be, we would just say clockwise and indicate it with this little, I call these little squirrely vectors. All right, so torque has units of Newton meter, and we generally don't call that a joule. Now, a very common case, right, is when the force makes some sort of angle. Right, so what I'm going to do here is I'm going to get rid of this stuff. And imagine now that I'm going to replace this with a single force. Maybe like this. Whoops, let me go back and redo that. I got a reason for wanting that to not quite look like that. Actually, I'll imagine it like this. There we go. So we're going to replace it with a single force vector that makes an angle theta, let's say with this distance. Now, we can't just take this force times this distance anymore because they don't make a right angle, right? When you do torque calculations, the force and the distance always have to make a right angle. There's two ways we can make that happen. Method number one, we can break this force into components like we always would, or like we do quite a bit in physics. Right? It's got a component this way, and it's got a vertical component. Oops, can't see the angle here. Oh, there we go. This is the component that's parallel to the distance, and it's equal to F cosine theta. This is the component that's perpendicular to my green distance. It's equal to F sine theta, but we're not going to need it anyway. Also, in vector diagrams, I usually put like the X component here, maybe the Y component here. I put it over here because this is where the force is applied. Now, when calculating the torque, when I compare these two components, we take the one that's perpendicular to the distance, that's this one right here, times the distance d. So this is the one that's creating the torque. This doesn't create any torque about this point, so the torque here would equal F sine theta times d. Now, this force makes a right angle to the distance I use, which is perfectly fine. There's kind of an alternative way I could have done this. We also rather than breaking the force into components, what you can do is you can kind of like break the distance into components, right? Forces have what's called a line of action. This force acts all along this green line right here. And what we can do is, if we can find this distance, the distance that's perpendicular to the line of action, then what we can do is take this force times this distance to calculate the torque. And if you'll notice, and again, let me do this in blue just shortly. Look at this triangle right here. Might not be perfect right triangle, but I had intended that to be a perfect right triangle. The hypotenuse is D. This side is opposite theta. That makes this perpendicular distance equal to D sine theta. So what we can do is take the entire force F times the perpendicular distance here, which is D sine theta, and that also gets us the torque. You'll notice that these two expressions here and here are equivalent. So whether you break the force into components and take the perpendicular force component times distance, or you find the distance that's perpendicular here to the force's line of action, take this distance times this force, either one is perfectly acceptable. So again, let me reword that. You can find the force perpendicular to the distance and then multiply, so that'd be this force times this distance in this example. Or you can find the distance that's perpendicular to the line of action. Take that distance times the entire force. Either one correctly calculates the torque. Remember, torque is a vector. You should always give a direction. Generally speaking, you can just use these little squirrely vectors here. Clockwise or counterclockwise is typically good enough in most of these problems. Anyway, hope this video helped describe what torque is. Have a great day.